Today, we're gonna talk about cerebellum, the little brain. Little brain is part of the hindbrain or the rhombencephalon. The functions of the cerebellum includes following 5 main functions. The cerebellum controls muscle tone, coordination of goal-directed and spontaneous movements, posture and balance, eye movements, motor learning, and some cognitive functions, including language acquisition, riding a bike or riding a horse, and playing guitar or doing music. So at the beginning of some skill required functions, we put a lot of efforts to learn them. For example, it takes us a long time to learn a new language or to ride a bike or to ride a horse or to learn how to play a musical instrument. But after a while, we do this without even aware of them. And each hemisphere of the cerebellum influences motor activity on the ipsilateral, or the same side of the body. Now, we know that we have ascending pathways terminating in the cerebellum, cerebellar cortices. These ascending pathways are called posterior spinocerebellar and anterior spinocerebellar pathways, which are unconscious or subconscious pathways that terminate in the cerebellum. The posterior spinocerebellar pathways never taxate or cross from spinal cord to the cerebellum. And anterior spinocerebellar pathway, well, it taxates, but it shows double taxations. So at the end, the cerebellum receives and controls the ipsilateral half of the body. Again, we continue to the function of the cerebellum. So the cerebellum compares the motor plan created in the cortex with motor performance reported from the periphery and functions to smoothen and coordinate the movements. And there is a well-developed connection between the cerebral cortex and the cerebellar nuclei and the cortices. So through this connection, through this well-developed connection between the cerebellum and the cerebrum, the cerebellum smoothens and coordinates the body movements that we do throughout our daily activities. And also, there is a connection between the cerebral hemisphere and the brain stem nuclei, and between the brain stem nuclei and the cerebellum. So we have a corticopontine and pontine cerebellar connections. Okay, look at this picture here. When we try to put our shoes on while one of our leg is up, to do this, our cerebellum helps provide smooth, coordinated body movement. And our cerebellum helps provide smooth coordinated body movements to several other functions, like riding a horse, riding a bike, or playing guitar or any kind of musical instruments, doing sport, playing soccer, all kinds of those things. Our cerebellum do a perfect coordination among the muscles of our extremities and body. Okay, now if you look at the location of the cerebellum in the hindbrain, the cerebellum is located behind the pons and the medulla oblongata, and which are separated from the cerebellum, or cerebellum is separated from the pons and the medulla, or the medulla oblongata, between through the fourth ventricle. This is the fourth ventricle. And if you look at the surface of the cerebellum, as you see, it is highly convoluted, forming folds or folia. These folds are called folia, and they are oriented horizontally or transversely. Now, if you look at here, the cerebellum is connected to the brain stem, which consists of, from inferior to the superior bulbus, the medulla, pons, the bridge, and the mesencephalon, the midbrain. Look at here. These are the structures called pedungles, cerebellar pedungles. Cerebellar pedungles connect cerebellum to the brain stem. Now look at here. This is the superior cerebellar peduncle, inferior cerebellar peduncle, and middle cerebellar peduncle. Superior cerebellar peduncle connects cerebellum to the mesencephalon. Middle cerebellar peduncle connects cerebellum to the pons, and inferior cerebellar peduncle connects cerebellum to the medulla, Okay, and similar to the cerebrum, the cerebellum consists of a midline vermis. We don't see this vermis exactly in the cerebrum, but like cerebellum, the cerebellum has two lateral hemispheres. So these are the hemispheres, cerebellar hemispheres. And the cerebellum anatomically is divided into three lobes, which are the anterior lobe, illustrated in red, the posterior lobe, illustrated in green, and the fibulogeno-nodular lobe, that is depicted in blue. The vermis means worm in Latin. Again, here is now you're looking at the cerebellum from the posterior view. Here looking at the cerebellum from the inferior view. Now, here is the anterior lobe. This is the posterior lobe. Again, it is the anterior lobe. This is the posterior lobe. And this is the follicular-nodular lobe. Follicular-nodular lobe is the oldest, phylogenetically oldest part of the cerebellum. Now, if you look at the cerebellum at the anterior pole of the anterior lobe, there is a notch here. This notch is the anterior notch. As you see, it is wider and lodging the peck of pons and the medulla. And it is separated from them by fourth ventricle. By fourth ventricle, you can see the fourth ventricle. And there is also a posterior notch. This is the posterior notch, which is occupied by fold cerebelli. Fold cerebelli, which separates the two cerebellar hemispheres. And fold cerebelli is the extension of the dura mater surrounding the brain. Okay, now the structures labeled. Here is the anterior lobe, posterior lobe, anterior cerebellar notch, posterior cerebellar notch. Now you see the vermis. The vermis is here, and this is the lateral hemisphere. Lateral hemisphere. Now here is the central lobule. We name the vermis from anterior to the posterior, starting from the superior surface, then continuing on the inferior surface of the cerebellum. So here is the central lobule, then the culmen, which belong to the anterior lobe, and then the declive and the folium. As you see, these are parts of the superior vermis. Superior vermis. Now, each part of the vermis has a representation or the correspondence on the cerebellar hemispheres. Look at here. Here you have the quadrangular lobule, simple lobule. Now, there are some very prominent fissures that separate the cerebellar lobules. One of them is the primary fissure. Look at this one. This is the primary fissure. This primary fissure separates anterior lobe from the posterior lobe. And there is another fissure that is the horizontal or the transverse fissure. That is this post-lunate fissure. And okay, now you look at the inferior surface of the cerebellum. Inferior surface of the cerebellum. Now we continue to name the vermis of the cerebellum. Now here is the tuber, the pyramus, uvulae, and Well, this belongs to the posterior lobe. And here is the nodule, which belongs to the flagullar-nodular lobe. Flagullar-nodular lobe. And here you have the secondary. This is the secondary or post-pyramidal fissure. Again, it is the horizontal fissure. This is the tonsil, retrotonsillar fissure, and this fissure is the posterolateral or dorsolateral fissure, which separates flagullar-nodular lobe from the posterior lobe. Here you see the cerebellar pedungles, middle cerebellar peduncle, inferior cerebellar peduncle, and the superior cerebellar peduncle. And here is the superior medullary velum, and here is the inferior medullary velum. Okay, let's continue to the superior surface of the cerebellum. Superior surface of the cerebellum lies beneath tentorium cerebelli and has a right superior vermis plus a large cerebellar hemisphere on its side, plus primary and horizontal fissures. Primary, here is the primary fissure, and the horizontal fissure is right there. The primary fissure is a V-shaped fissure. It is well defined, lies on the superior surface, and separates the small anterior lobe from the larger middle lobe. But mostly we use the posterior lobe. You can call this the middle lobe because this posterior lobe is located between the anterior lobe and the flagullar-nodular lobe. So you can call this middle or posterior lobe. But posterior lobe is common to use. The horizontal fissure, which lies along the side of cerebellum, extending from anterior notch to the posterior notch, separates the superior from the inferior surface. Now, what you see here is the superior surface. Now this is the horizontal fissure, which separates the superior surface of the cerebellum from its inferior surface. Now let's look at the inferior surface of the cerebellum. Now it is rounded on its side, and as you see, it is rounded on its side and presents a deep groove, which is called a valleculae, between two cerebellar hemispheres, which is occupied by the inferior vermis and the tonsil. This is the tonsil, or the cerebellar pyramid. Tonsil, or the cerebellar pyramid. Now, the tonsil is a small part of the cerebellar hemisphere that lies lateral to the inferior vermis. It is the inferior vermis, so it is located lateral to the inferior vermis. Behind the tonsil, there is a fissure. which is called retrotonsillar fissure. As you see, this retrotonsillar fissure separates tonsil from the biventer lobule, biventer lobule. Now, there is another fissure here that is the secondary or posterolateral fissure, lies on inferior surface and separates. Look at this is the secondary or the posterolateral fissure, lies on inferior surface and separates flagellonatural lobe from the remainder of the cerebellum. Flagella secondary fissure, that is right here. Okay, we have seen this picture. The superior vermis contains the central lobule, culmen, which belong to the anterior or rostral lobe, declive, and the folium, which belong to the posterior lobe. Again, here is the primary fissure separating rostral lobe from the posterior or caudal lobe. Here is the horizontal fissure which separates superior surface of the cerebellum from its inferior surface. Simplex lobule is the rostral or superior semilunar lobule. Between them, there is the postlunate fissure. Here is the horizontal fissure. You can see it from the inferior view here. Posterior cerebellar notch, which is occupied by the cerebellar falx. Falx means auricle. Now you see the external fissures on the inferior surface of the cerebellum. Now here you see the inferior vermis, which contains the tuber, pyramid, uvulae that belong to the posterior or the caudal lobe of the cerebellum. And here you have the nodular part of the flagellonatular lobe. And here is the dorsolateral or the posterolateral fissure, which separates the flagellonatural lobe from the tonsil. Behind the tonsil, you see there is a fissure here. This is called retrotonsillar fissure. This is the biventer lobule. Down here you have the caudal or the inferior semilunar lobule. And there is the secondary or the post-pyramidal fissure here. Again, this is the inferior medullary velum, superior medullary velum, which surrounds the fourth ventricle. Look at, here is the superior medullary velum, inferior medullary velum, which surrounds the roof of the fourth ventricle, the superior medullary velum superiorly, inferior medullary velum inferiorly. Okay, here the uvula means little grape and the tuber means swelling. Again, now we open the cerebellum, and what you see here is in the midline, there is the vermis. This part is the hemisphere, anterior lobe, posterior lobe, and the nodular lobe. Here is the primary fissure. Here is the horizontal fissure. Here is the posterior fissure, and flagellus. Again, you see the middle cerebellar peduncle connecting pons to the cerebellum, superior cerebellar peduncle connecting mesencephalon to the cerebellum, and the inferior cerebellar peduncle that connects medulla oblongata to the cerebellum. Here is the acoustic nerve or the vestibulocochlear nerve, the cochlear nerve. Here is the trigeminal nerve, the pons, mesencephalon, and the medulla, the pyramid, olivary body. We continue to the external features of the cerebellum. What you see here is the vermis. Here is the vermis. We number the parts of the vermis starting from the anterior part of the superior vermis, going posteriorly, then turning on the inferior view or the inferior side of the vermis. Okay, the lingulae, and here is the central lobule and the culmen, then declave, folium, tuber, pyramus, and uvula, and nodulus. Here is the vermis. Lateral to the vermis is the paravermis, and the hemisphere, So part of there is a correspondence of each part of the vermis on the cerebellar hemisphere. Lingulae, its correspondence or its continuation on the cerebellar hemisphere is the vingulum lingulae. It is the continuation of the central lobule on the cerebellar hemisphere is the ala lobulus centralis. For the culmen, it is anterior quadrangulate lobule. For the declave, it is the posterior quadrangular lobule. For the folium, it is the superior semilunar lobule and the inferior semilunar lobule. And then for the tuber, it is the gracile lobule. For the pyramus, it is the again the gracile lobule. For both tuber and the pyramus, it is the gracile lobule. Then for the uvulae, it is the biventral lobule and the tonsil. For the nodulus, it is the flagellus. For the number, for the lingulae, you have the 1. For the central lobule, 2 and 3. For the culmen, 4 and 5. For the decleve, it is 6A, B, and C. For the folium, it is 7. For the pyramus, it is 8. For the uvulae, 9. For the nodulus, it is 10. Okay. Now let's look at the sagittal view of the cerebellum, starting from the superior medullary velum. Here is the superior medullary velum. Right behind the superior medullary velum, you have the lingulae of superior vermis. This is the central lobule of superior vermis. Then this is the culmen of superior vermis, 4 and 5. And then here is the decleve of superior vermis, 6. And this is the folium here, the folium of superior vermis. Now we continue on the inferior vermis from now here on. Tuber of inferior vermis, pyramid of inferior vermis, uvulae of inferior vermis, and the nodulus of inferior vermis. Note that the nodulus is located right behind the inferior medullary velum. Again, the same structures you see. Here is the superior medullary velum, lingulae, central lobule, culmen, decleve, folium, tuber, pyramid, uvulae, and the nodulus. And you see the numbering beside each part of the vermis. Again, here is the 4th ventricle. This is the inferior medullary velum, superior medullary velum. Right behind the superior medullary velum, you have the lingulae. Right behind the inferior medullary velum, there is the nodulus. So this might help you to list parts of the superior vermis and inferior vermis. Now this is a section in plane of superior cerebellar peduncle. Here is the superior cerebellar peduncle. You see the decussation of superior cerebellar peduncles. superior cerebellar peduncle. What you see here is the medial longitudinal fasciculus. Medial longitudinal fasciculus, remember, connects the nuclei of oculomotor, trochlear, abducens, and vestibular cochlear nerves. And here is the superior cerebellar peduncle, superior cerebellar peduncle, superior medullary velum, and you see the cerebellar nuclei. We're gonna look at the cerebellar nuclei in detail, but just broadly, let's name them here. This is the vestigial nucleus from inside the outside. You have this vestigial nucleus. Then lateral to it, you have the globose nuclei. Then the emboliform nucleus. Then the dendate nucleus. These are the cerebellar nuclei. Cerebellar nuclei. Efferents, or the cerebellar efferents, originate from this nuclei. Again, here is the vermis. Here is the vermis, the cerebellar hemispheres, and the cerebellar peduncles, superior, middle, inferior peduncles. These are the cerebellar nuclei from inside to outside. These nuclei are the vestigial nucleus, globose nucleus, emboliform nucleus, and the dendate nucleus. Primary fissure. Primary fissure. Here is the tonsil. That is the tonsil. Fourth ventricle and the superior medullary velum, and you see the lingulae, part of the superior vermis. Okay, the same dendate nucleus from outside to inside. These are the deep nuclei of the cerebellar cortex. From outside to inside, the dendate nucleus, emboliform nucleus, globose nucleus, and the vestigial nucleus. These are the deep nuclei of the cerebellum. Okay? Now here you have the interposed nucleus. Now the vestigial nucleus controls the stance and gait, and also the controls muscles only in the modes of sitting, standing, and the walking. Then the globose and emboliform nucleus together, this control the segmental reflexes, speeds the initiation of movements triggered by somatosensory cues that guide the response, stops unwanted and promotes wanted oscillations, and stabilizes holds. The dendate nucleus here is responsible for the planning, initiation, and control of voluntary movements. The motor function, which is the movement of skeletal muscle, non-motor function, such as conscious thought and visuospatial function. As you see, the cerebellar nuclei are the nuclei where the cerebellar efferents originate and controls several important functions relating to the balance, including controls of muscles in the modes of sitting, standing, and walking. These efferents originate from the vestigial nucleus and then segmental reflexes, speed of the initiation of movements triggered by somatosensory cues that guide the response, stops unwanted movements, and promotes wanted oscillations, and also stabilizes the holds. Look at the dentate nucleus here, which the efferents originating from the dentate nucleus are responsible for the planning, initiation, and control of voluntary movements. When we talk about motor function of the cerebellum, actually we talk about the movement of the skeletal muscle. When we talk about the non-motor function, we talk about conscious thought, planning, and also the visual-spatial function. Now let's look at the subdivision of the cerebellum. Now, this schematic drawing of cerebellum showing the relationship between the anatomical and functional divisions of the cerebellum. Now, the spinocerebellum is this one. Here is the neocerebellum. This is the vestibulocerebellum. So the oldest part of the first part of the cerebellum that develops during the embryonic life is the vestibulocerebellum. This is called also the archicerebellum, the oldest part of the cerebellum. And then the vermis and surrounding cerebellar hemispheres, this part is called the spinocerebellum. Phylogenetically, this is the paleocerebellum. Functionally, spinocerebellum. Flagullonodular lobe is the vestibulocerebellum, functional vestibulocerebellum, and phylogenetically, this is the archicerebellum, the oldest one. And functionally, the lateral parts of the cerebellar hemispheres are the cerebrocerebellum. This is the functional division, and this is the newest part of the cerebellum. So the neocerebellum. This part of the cerebellar hemispheres developed newly. So during the embryonic life, this part of the cerebellar hemispheres developed later on. Okay, here is the cerebrocerebellum, spinocerebellum, and the vestibulocerebellum. These are the functional subdivisions of the cerebellum. Flagullar lobe actually forms the vestibulocerebellum, and the efferents originating from vestibulocerebellum terminate in the vestibular nuclei to control balance and eye movements. Now the vermis and surrounding cerebellar hemispherical parts, as you see here, project to the medial descending systems. The vermis part project to the medial descending systems, and the part of the cerebellar hemisphere adjacent to the vermis, this area, the efferents originating from here, project to the lateral descending systems. Both medial and lateral descending systems controls or initiates motor execution. And this is the cerebrocerebellum, or the phylogenetic, that is the neocerebellum, which projects to motor and premotor cortices of the cerebrum for motor planning. Again, now what you see here, this include the visual and auditory impulse and the vestibular inputs. So what you see here, these are the afferents coming to the cerebellum. Corticopontine inputs terminate in the vestibulocerebellum and cerebrocerebellum. And spinal and trigeminal inputs terminate in the vermis or the in the spinocerebellum. So the spinocerebellum receives spinal and trigeminal inputs. And cerebrocerebellum and the vestibulocerebellum receive corticopontine inputs. Now let's look at the afferent or output of the cerebellum. So the vestibulocerebellum project to the vestibular nuclei for balance and eye movement, and spinocerebellum, its vermis part projects to the medial descending systems. Its lateral part projects to the lateral descending systems. Together, controls the motor execution. So the spinocerebellum controls motor execution. And the cerebrocerebellum, which is the lateral hemispheres, projects to the motor and premotor cortices of the cerebral cortex for motor planning. Again, the same things here. The vermis and intermediate hemisphere together make up the spinocerebellum, which the vermis part of the spinocerebellum projects to the vestigial nucleus, whose efferent project to the medial descending pathways or the systems, and the intermediate hemispherical part of the spinocerebellum project to the interposed nucleus, which then project to the efferent starting from the interposed nucleus project to the lateral descending systems for the motor execution. And look at here, efferents starting from the vestibulocerebellum projects to the vestibular nuclei. Then this vestibular nuclei, through their efferents or the motor pathways, connect the balance and eye movements. Now let's look at the cerebrocerebellum, which the dentate nucleus, through the dentate nucleus, cerebrocerebellum controls the efferents initiating from the dentate nucleus terminate in motor and premotor cortices, which control the motor planning. Okay, archicerebellum, it is also called the posterior lobe or the vestibular part. Archicerebellum is this one here. It is formed of the flagullar-nodular lobe plus associated vestigial nuclei lying on inferior surface in front of posterolateral fissure. Embryologically, flagullar-nodular lobe is the oldest part of the cerebellum. It receives afferent fibers from vestibular apparatus of internal ear through vestibulocerebellar tracts. It is concerned with equilibrium and eye movements. Now the archicerebellum, it is concerned with equilibrium. It represents flagullar-nodular lobe. It has connections with vestibular and radicular nuclei of brainstem through the inferior cerebellar peduncle. The afferent vestibular fibers pass from vestibular nuclei in pons and medulla to the cortex of ipsilateral flagullar-nodular lobe. Now let's talk about the efferent cortical or the Purkinje cell fibers project to the vestigial nucleus, which projects to vestibular nuclei and radicular formation. Now this system affects the lower motor system bilaterally via descending vestibulospinal and reticulospinal tracts. This is how cerebellar efferents or motor pathways initiating from the archicerebellum controls lower motor system through these tracts. Okay, paleocerebellum or the spinal part, which formed of midline vermis and surrounding paravermis, plus globose and envelopform nuclei. And spinal part receives afferent proprioceptive impulses from the muscles and tendons via spinocerebellar tracts, the dorsal and ventral mainly. And this spinal part sends its efferents to red nucleus of midbrain, and spinal part is concerned with muscle tone. The paleocerebellum is concerned with muscle tone and the posture. The afferent spinal fibers to the paleocerebellum consist of dorsal and ventral spinocerebellar tracts from muscle, joint, cutaneous receptors to enter the cortex of ipsilateral vermis, paravermis via inferior and superior cerebellar peduncles. For the efferents cortical fibers, they pass to globus and ampelliform nuclei, then via superior cerebellar peduncle to contralateral red nucleus of midbrain to give rise descending retrospinal tract. And the neocerebellum, it is the remaining largest part of the cerebellum, which includes the most of two cerebellar hemispheres plus the dentate nucleus. And cerebral part of the cerebellum receives afferent impulses from the cerebral cortex and tones via cerebropontocerebellar pathway. And the neocerebellum sends its efferents to the VL nucleus, ventrolateral nucleus of thalamus. And neocerebellum controls voluntary movements, the muscle coordination during the voluntary movements. Okay, the neocerebellum is concerned with muscular coordination, receives afferents from the cerebral cortex, involved in planning of movement to pontine nuclei, cross the opposite side via middle cerebellar peduncle to end in lateral parts of cerebellum. This is called cerebropontocerebellar tract. Let's look at here. Cerebropontocerebellar tract. And there are the neocerebellar efferents, which project to dentate nucleus, which in turn projects to the contralateral red nucleus, then the motor cortex of frontal lobe, giving rise descending corticospinal and corticobulbar pathways. The efferents of dentate nucleus form a major part of the superior cerebellar peduncle. Now, the superior cerebellar peduncle, which is this one here, this superior cerebellar peduncle connects with the midbrain, middle cerebellar peduncle connects with the pons, inferior cerebellar peduncle. It's also known as restiform body, connects with the medulla. And this superior cerebellar peduncle is also known as brachium conjunctivum. And the middle cerebellar peduncle is also known as brachium pons. Superior cerebellar peduncle contains afferents, ventral spinocerebellar tract, which transmits proprioceptive and exteroceptive information from levels below the mid-thoracic cord. The tectocerebellar tract arises in the superior and inferior colliculi, superior and inferior colliculi and carries auditory and visual information. Auditory information through the inferior colliculus and visual information through the superior colliculus. Now, inside the cerebellar peduncle, another afferent that way is the trigeminal-cerebellar tract, which carries proprioceptive fibers from the mesencephalon and the tactile information from the principal or the chief nucleus of the trigeminal nerve. Another afferent tract inside the superior cerebellar peduncle is the cerebellar tract. These fibers come from the nucleus ceruleus. Now, the efferents that are found inside the superior cerebellar peduncle include the dentatorubral tract, output to the contralateral reticulus, dentatorthalamic tract, output to the contralateral ventrolateral nucleus of the thalamus, and uncinate bundle of Russell, output to the vestibular nuclei and reticular formation. Cerebellar peduncles actually contain afferent and efferent cerebellar tracts. Superior cerebellar peduncle contains following afferent tracts: ventral spinocerebellar tract, tectocerebellar tract, trigeminocerebellar tract, the cerebellocerebellar tract. The ventral spinocerebellar tract transmits proprioceptive and exteroceptive information from levels below the mid-thoracic cord. In other words, from the lower body, lower half of the body. Tectocerebellar tract arises in the superior and inferior colliculus and carries auditory information from the inferior colliculus and visual information from the superior colliculus. The trigeminocerebellar tract carries proprioceptive fibers, so the proprioception from the mesencephalon and tactile information from the sensory or main or chief sensory nucleus of the trigeminal nerve. The cerebellar tract contains fibers originating from the nucleus ceruleus. Remember, this nucleus is found in the locus ceruleus, that is located in the superior fovea at the upper end of the sulcus limitans, main source of noradrenaline or the norepinephrine produced in the central nervous system. The efferents that superior cerebellar peduncle contain include dentatorubral tract that is output to the contralateral reticulus, dentatorthalamic tract output to the contralateral ventrolateral nucleus of the thalamus, or the VPL nucleus of the thalamus. Again, this efferents initiate or originate from the tendate nucleus, in this case, tendate nucleus, and terminate in the red nucleus. Originate in the tendate nucleus, terminate in the VPL of the thalamus. That's why the name is tendatorectal tract and tendatothalamic tract. The uncinate bundle of Russell is the output to the vestibular nuclei and reticular formation in the brain stem, basically over the medulla, pons, and the mesencephalon. Now, the middle cerebellar peduncle. Middle cerebellar peduncle contains only afferent fibers, but no efferent fibers. Now, the pontocerebellar tract arises in contralateral pontine gray matter. Now, these afferent fibers are also known as the corticopontocerebellar tract. This corticopontocerebellar tract actually originates in the cortex, cerebral cortex, then project to the pontine nuclei or the pontine gray matter in the brain stem. Now, in the pontine gray matter, there are neurons. Their axons cross the midline and terminate in the cerebellar cortex. That's why this pathway is called corticopontocerebellar tract or fibers. Through the corticopontocerebellar fibers, cerebellum receives cortical inputs from the cerebral cortex, and this transmits impulses from the cerebral cortex to the intermediate and lateral zones of the cerebellum. Okay, now let's look at the inferior cerebellar peduncle. Now, inferior cerebellar peduncle contains many afferent tracts. These are dorsal spinocerebellar tract, cuneo-cerebellar tract, olivocerebellar tract, vestibulocerebellar tract, reticulocerebellar tract, arcuatocerebellar tract, and trigeminocerebellar tract. Let's look at these afferents one by one. The dorsal spinocerebellar tract originates in the dorsal nucleus of Clark between T1 and L2 and carries proprioceptive and exteroceptive information, mostly from the body and ipsilateral lower extremity. Cuneo-cerebellar tract originates in the external arcuate nucleus, which transmits proprioceptive information from the upper extremity and the neck. Olivocerebellar tract carrying somatosensory information from the contralateral inferior olivary nuclei of the olive. Vestibulocerebellar tract that transmits information from vestibular receptors on both sides of the body. Reticulocerebellar tract arises in the lateral reticular and paramedian nuclei of the medulla or the medulla oblongata. The arcuatocerebellar tract arises from the arcuate nuclei of the medulla oblongata. The last afferent tract is the trigeminocerebellar tract, arises from the spinal and main sensory nuclei of trigeminal nerve, which brings sensory information from head and face to the cerebellum. And the efferents that are found in the inferior cerebellar peduncle include fastigiobulbar tract and cerebello-reticular pathways. Now, the cerebellum influences movements via connections to both the brain stem and cerebral cortex. Look at here, cerebellum influences movements via connections to both the brain stem and to the cerebral cortex via the thalamus. So the cerebral cortex, cerebral motor cortex, control motor innervation through the direct activation pathways. So the cerebral motor cortex controls the brain stem and also controls the spinal cord, controls the brain stem through the corticobulbar pathways, and the spinal cord through the corticospinal pathway. And then cerebellum receives information from the brain stem and also from the spinal cord. Indirect activation pathways from brain stem to the spinal cord are the rubrospinal, vestibulospinal, reticulospinal, tectospinal pathways. So through these pathways, brain stem controls the spinal cord. Then cerebellum receives sensory information from the spinal cord and the brain stem, and cerebellum also receives inputs from the cerebral motor cortex. That's how cerebellum controls movements, coordinated, integrated, balanced movements throughout our skeletal muscles. Now let's look at the vascular supply to the cerebellum. There are three vessels that supply to the cerebellum. One of them is the pica, posterior inferior cerebellar artery, which is here. Pica supplies to inferior 1/3 of the cerebellum. Pica is a branch to the vertebral artery. And then the ICA, anterior inferior cerebellar artery, which is a branch, actually first branch to the basilar artery that supplies middle 1/3 of the cerebellum. And superior cerebellar artery supplies the upper 1/3 of the cerebellum. And superior cerebellar artery is an artery to the basilar artery as well. Okay, look at here. The vertebral artery arises from the subclavian artery in the neck and then ascends through the foramen, transverse foramen of the cervical vertebrae and pass through the foramen magnum, and before joining and forming the basilar artery, Each vertebral artery gives off posterior inferior cerebellar artery, this one, which supplies the inferior 1/3 of the cerebellum. The two vertebral arteries unite in the lower border of the pons and form the basilar artery. And the first branch of the basilar artery is the AYCA, anterior inferior cerebellar artery, which supplies the middle 1/3 of the cerebellum. And then the superior cerebellar arteries, a branch to the basilar artery that supplies the upper 1/3 of the cerebellum. Okay, you see which artery supplies which part of the cerebellum. This is the superior cerebellar artery. Here is the posterior inferior cerebellar artery. It is the AYCA, the area supplied by AYCA, the area supplied by PICA. This area is supplied by the SCA, superior cerebellar artery. Here is the superior cerebellar surface. Here represents the inferior cerebellar surface. The cerebellar nuclei, just reiterate them: tendate, emboliform, globose, and the vestigial nucleus. Here is the anterior lobe, primary fissure, posterior lobe. Here is the flagullonodular lobe, its flagellus, its nodulus, the peduncle of flagellus, peduncle. And here is the posterolateral fissure. The area indicated in green supplied by the superior cerebellar artery, the area indicated in red supplied by posterior inferior cerebellar artery, the area indicated in blue is supplied, indicated in yellow, supplied by the AYCA, anterior inferior cerebellar artery. Again, the area indicated in green supplied by the SCA, in yellow supplied by the AYCA, in red supplied by the PICA. Now, the section A taken through the inferior border of the cerebellum, and section B is taken through the middle of the inferior part of the cerebellum, and section D is taken through the upper end of the superior cerebellum, and this is section C is taken deep to the superior cerebellum. Okay, the PICA, posterior inferior cerebellar artery, from intracranial vertebral artery, supplies the lateral medullary tegmentum, inferior cerebellar peduncle, the ipsilateral portion of inferior vermis, and inferior surface of the cerebellar hemisphere. Its medial branch supplies dorsolateral medulla and medial cerebellum. Lateral branch supplies inferior posterolateral. The AYCA, which is this one, anterior inferior cerebellar artery, it originates from the basilar artery, supplies to the anterior petrosal, surface of the cerebellar hemisphere, flagellus, lower portion of the middle cerebellar peduncle, and lateral pontomedullary tegmentum. Superior cerebellar artery, this one here, it is a branch to the basilar artery. It arises from the basilar artery just below the trigeminal bifurcation into the paired posterior cerebellar artery and supplies to the upper surface of the cerebellar hemisphere, ipsilateral portion of superior vermis, most of the dentate nucleus, upper portion of the middle cerebellar peduncle, superior cerebellar peduncle, and lateral pontine tegmentum. What happens in the lesions of the cerebellum? Well, cerebellar lesions are usually vascular, maybe traumatic or tumor-related. Manifestations of unilateral cerebellar lesions, well, causes ipsilateral incoordination of upper limb or the arm. This is called the intention tremors. And it is a terminal tremors at the end of movement, as in touching nose or the button, the T-shirt. And it causes also ipsilateral cerebral ataxia, affects lower limbs, the leg causing the wide-based unsteady gait. Manifestations of bilateral cerebral lesions, which is caused mainly by alcoholic intoxication, cerebellar degeneration, multiple sclerosis, and hypothyroidism. And dysarthria is the slowness and slurring of speech. So speech becomes slurry and slow. Okay, so the incoordination of both arms, the intention tremors, cerebral ataxia, intermittent jerky movements, or staggering, wide-based, unsteady gait. Nystagmus, it is due to impairment, coordination of eye movements. So incoordination of eye movements occurs and eyes exhibit a to and fro motion. Combination of nystagmus, dysarthria, and intention tremors constitutes Charcot's triad, which is highly diagnostic of the cerebral lesions. So this loss of cerebellar function does not produce paralysis or the inability to initiate a movement. Rather, cerebellar disease produces disturbances in the coordination and fine control movement and posture. Remember, initiation of a movement controlled by the primary and premotor cerebral cortex. Therefore, loss of cerebellar function or the cerebellar lesions do not produce paralysis or inability to initiate a movement. Rather, the lesions or the cerebellar lesions produces disturbances or the impairs the coordination and fine or the delicate control of movements and the posture and also the gait.